So we've looked pretty in depth at passive cooling strategies so far, and passive cooling strategies are, of course, a great idea to implement on any project, whether you have an active cooling system or not. They're going to help you reduce energy consumption and improve comfort for the occupants. So we highly recommend implementing all of the passive strategies that you possibly can, but in many climates, especially humid climates, you're going to have to resort to active cooling in order to provide thermal comfort, especially humid climates like that part of the eastern United States where I work. So we do a lot of active cooling systems, not at all unusual in a place like New York City to have these types of active cooling systems. So let's dive a little bit in depth in active cooling. We'll talk a little bit about the basics of how active cooling energy demand is calculated. We'll talk about moisture, and then we'll talk about some cooling equipment before we turn our attention back to the PHPP and look at how we model these cooling systems. So when it comes to the PHPP, we know that the PHPP kind of operates by asking questions and specific and answering specific questions. So the specific question that we want the PHPP to ask or answer for our purposes is, please calculate the total energy needed to cool the building over the summer period. So how is the PHPP going to do that? It's going to do it in a very similar way to how we've calculated heating energy consumption. If you look at the equation there, that equation looks very similar. In order to calculate the total cooling energy demand, we're first going to calculate the total solar gain, the total internal gain. We're going to add those together. Then we're going to subtract from those the total transmission losses and ventilation losses, all of those assessed over the cooling period. In this case, notice we're going to multiply the Q sub T and Q sub V by an eta, ETA, Greek letter eta, an efficiency or utilization factor for the cooling period. And that's going to yield to us a total cooling energy demand over the cooling period. And all of those pieces are going to get calculated the same way that we've already looked at. So calculating solar gain, calculating internal gain, calculating transmission loss, calculating ventilation loss, those are all going to be done using the same methods and the same inputs as before, except that we're going to do them over the cooling period rather than over the heating period. And that's going to be the big difference. So over the cooling period, in this case, notice that the heat gains are going to outweigh the heat losses. So we need to add losses to the system in order to balance out the energy balance equation. How do we add losses? That's a weird way to say that. How do we add losses to a building? Well, that's an air conditioning system. We're going to take heat out of the building by using some sort of equipment. We're going to add additional losses to the building. Now, of course, this is looking at the building over the course of a whole year. The PHPP, in actuality, is going off and doing a series of monthly calculations. So when it comes to the sensible cooling energy demand, it's going to do that calculation on a monthly basis and then just sum up all of the results there to give us a total cooling energy demand over the cooling period. Now, when it comes to certification, though, we're going to look at the total annual result. So when it comes to certifying our building has to be below that 4.75 kBTU per square foot per year or 15 kilowatt hours per square meter per year energy demand threshold. Now, interestingly, though, if that's the demand limit, if that's the demand threshold for PHI certification, why, when I look at my PHPP, does it show a limit of 5.39 kBTU per square foot per year? Why doesn't it show 4.75? Well, what PHI has determined over the years is that if you're in a very, very humid location, there are very few things that you can do to reduce the amount of energy needed to dehumidify your building. There are almost no levers available to you as a designer to modify the shell or the envelope of the building in a way that helps reduce that dehumidification need. dehumidification need in most buildings is really just a function of your climate. You do have some levers, and we'll talk about them, but they are very few and far between. And so, what PHI has said for certification purposes is okay, meet that 4.75 sensible cooling energy demand limit, and then depending on how humid your climate is, there will be an additional allowance for that so-called latent cooling demand energy, the amount of energy needed to dehumidify the building. And that limit is going to change depending on climate. So depending on where you are in the world and how humid your location is, you will have a higher or lower total annual cooling energy demand limit for a certified passive house building. If you're in a very dry climate, like the desert Southwest in the United States, or maybe Spain, Melbourne, Australia, you're going to have a total annual demand limit of 4.75. You don't get any additional allowance for dehumidification. It's not really needed in a climate like that. Now, New York City, where I practice, I complain about it being a humid location. It's really not, all things being relative. Places like Beijing, Shanghai, Miami, Acapulco, there are many places that are much, much more humid than places like New York, of course. So as much as we complain about it, it's really not that bad, all things considered. So depending on where you are in the world, you might have a higher or lower annual cooling energy demand limit that you're supposed to meet, that you're supposed to achieve for a certified passive house building. So let's talk a little bit about moisture, because obviously moisture is going to be an important piece of the puzzle here. So where is all this moisture coming from? Why do we have this dehumidification load? And what can we do about it? Can we reduce that energy demand? And of course the answer is yes. But let's start with where the moisture is coming from. So the moisture comes from three primary places. So first of all, if you're in a humid climate, you have a lot of moisture in the air outside the building. There's going to be a bunch of moisture coming into the building, riding on air leaks. So if you have air leaks through your envelope, and of course we're not building space shuttles, we're still building buildings, there will be some amount of air leakage, 0.6 air changes per hour worth of air leakage. Riding on those air currents will be a bunch of moisture. So you're going to have unintentional moisture or unintentional airflow, and then moisture coming in as a result. Now, of course, we also, though, have a bunch of intentional air exchange. We have a machine, an HRV, an ERV, some sort of ventilator with some fans, which is taking outdoor air and bringing it right into our building. And it's going to be doing that all summer long. It's going to be doing that because people have a nasty habit of doing things like breathing all summer long. And so that ventilator machine is going to be operating all summer long, and then riding on that ventilation airflow will be a bunch of moisture. And then lastly, we have a bunch of moisture from stuff that people do inside of buildings. Things like cooking, things like bathing, things like washing dishes, breathing, respirating, these types of things release moisture into the air in the building itself. So we have three distinct sources of moisture that we want to try and manage, or that we need to combat, in order to deliver an acceptable level of humidity inside of our buildings. Remember, that acceptable level is put at 0.012 pounds of moisture per pound of dry air. So that begs the question, of course, well, what happens if the air that's coming in is at a much higher level of humidity? What if the air in the summertime that's coming into my building through the ERV is at 85, 90 degrees Fahrenheit? 30 degrees Celsius? And what happens if it's at 70, 60, 70% relative humidity? So a much higher absolute humidity. Well, of course, the answer there is that in order to deliver comfort, our active dehumidification is going to have to strip that moisture out of that air. Call it dehumidification. And that act of stripping that moisture out of the air takes energy. And so in order to properly dehumidify that incoming air, we're going to need to expend energy in order to make the building comfortable. Remember, this is primarily a function of your outdoor climate. So depending on how humid it is outdoors in the summertime in your climate, you'll have more or less energy expended for this purpose. So if those are our three sources of moisture, what can we do to combat those things? Well, obviously, if we have a bunch of moisture leaking in through air leaks, it stands to reason that the more airtight we make our building, the lower the moisture load, the more comfortable the building, the less energy we expend on dehumidifying the building. And of course, that is true as well. Here we're measuring peak moisture load in grains of moisture per hour. A grain is a silly old time unit for measuring moisture. It's like I don't remember, 1/7,000th of a pound or some such nonsense. Anyway, it's just an old fashioned measurement of moisture. So you can see here clearly the moisture load reducing significantly as we increase the airtightness of the building. As we move from a very leaky envelope towards a very airtight envelope, we're going to reduce the amount of moisture leaking in significantly. So airtightness can definitely help. Now an ERV can also help. So this is one of those scenarios where the energy recovery ventilator can help significantly. If we have a nice, cool, dry interior environment and we have a very hot and humid outdoor environment, in that scenario, if we still want to bring fresh air into the building, because of course we do, because we want healthy indoor environments for the people who live in our buildings, we have to somehow strip the moisture out of that incoming airstream. Well, an ERV, as opposed to an HRV, is able to do just that. So in an ERV, an energy recovery ventilator, the moisture from that relatively humid incoming airstream is able to transfer, is able to hop from that wet airstream over to the dry outgoing airstream. And functionally speaking, what that does is it keeps most of the moisture on the outdoor side of the ERV. Now, it's not perfect. Even the best ERV available is only something like 50 or 60% efficient, meaning only 50 or 60% of the moisture is able to be transferred from one airstream to another. But that's still 50 or 60% less moisture coming into your building, significantly improving thermal comfort and reducing the energy expenditure needed for dehumidification. So in many humid climates, an ERV in summertime is a great idea. It keeps that moisture out of the building while still allowing us to supply fresh air into the space. Now, the last piece of the puzzle there, the people, there's really not very much you can do about the people. It's not like you're going to get them to breathe less or bathe less or do any less cooking or anything like that. The moisture loads that come from people just kind of are what they are. And it's relatively straightforward the way that flows through. All the things that people do, depending on the number of people in the building, are going to translate into a certain amount of moisture released into the air of the building. So what does that mean if we put it all together? Well, it means that we've got three sources of moisture and really only two levers to affect the total latent load or the total latent energy demand of our building. We can reduce or improve the air tightness of the building. That's going to reduce the amount of moisture leaking in from outdoors in the summertime. That's a good idea. We can use an ERV instead of an HRV, and we can use a really efficient one with a high moisture recovery rate. That's a good idea. But then that last piece, the people, the internal sources, there's really nothing we can do about that. That's just people living their lives in the buildings. And what we're left with there is, in some cases, depending on the climate, a pretty significant amount of energy needed to dehumidify our buildings, to get our buildings down to that target humidity level. And that, of course, is where most of us stand, as I've said several times, in the eastern part of the United States, certainly in the part of the country that I work in. And that's where cooling equipment comes into the picture. Active cooling equipment, which is going to allow us to both cool the building and dehumidify, is incredibly important in many parts of the world. Now, when it comes to the PHPP, we have the opportunity to model a combination, one of or a combination of four distinct types of cooling equipment. So the PHPP will allow us to model so-called supply air cooling. We'll talk a little bit more about that in a second. Recirculated cooling, that's sort of good old-fashioned air conditioning. Additional dehumidification, so dedicated standalone dehumidification, a great idea in many humid climates, or panel or radiant cooling, certainly a good option in some climates, in particular climates that don't have high humidity loads, because of course with cold surfaces you're going to run a condensate formation risk. So let's take a look at the sort of two main elements here that we might, or let's take a look at the first two options here, and we'll sort of talk about those and sort of, especially that supply air cooling. What are they talking about when they talk about supply air cooling? Well, of course, I'm sure you all remember from your passive house training that the original definition of a passive house, the original idea behind what a passive house was and how a passive house was supposed to operate, was that a passive house didn't have or wouldn't have an active heating system per se. Instead, it would have a ventilation system, an ERV or an HRV, and then you might have a simple post heater, which would add some heat to that ventilation airstream, and then you would supply all the heating needed for the building, riding on the ventilation air. It was a neat idea. It was a cool idea. We've never done anything of the sort. By the time the passive house standard arrived in the United States, we were already sort of not doing that. And so we don't do that anymore. But that was, or at least we don't do that anymore in the United States. There are plenty of climates and plenty of locations where that still is a viable idea, where people are still trying to do that. We do not. So that's a neat idea, though. Sometimes, maybe, it could work, kind of, in some circumstances. But what about cooling? So in particular, if you're in a climate where you need to both heat the building and cool the building and dehumidify the building, could you do something like that through the ERV? Is that a viable strategy? Would that ever work? And in humid climates, the short answer is no, definitely not. We've looked at this on several projects. This is just one example of a project from many years ago that we were assessing this strategy. It's a large building here in Manhattan. And on the left-hand side there, you can see the modeled peak heating loads and peak sensible and latent cooling loads. So the red, obviously heating, and the blue, the dark blue, sensible cooling, and the light blue, latent cooling, dehumidification. Those are the modeled loads for the building, and then the lines there, the red lines there, are showing the maximum load transferable through the fresh air system, through the ERV. And notice that, interestingly, because of the density and the glazing and the insulation on this building, you actually probably could have done all of the heating supply through the ERV if you could ever figure out how to do controls properly. You probably could, from a strictly, energy sense, energy in, energy out sense, you probably could have delivered all the heating through the ERV. But on the cooling side, notice that you're like 3x, like 300% what you could actually deliver through the ERV. You're not even within spitting distance. There's not even really any reason to consider it. It just doesn't make any sense, especially in a place like New York where we have a lot of dehumidification need. Again, if you don't have that dehumidification need, maybe you could consider it, although again, probably not. The reality is that we just can't cool that supply air very far. And so the delta T, the difference in temperature, the amount of energy that we're able to transfer through the ventilation system is just not very big. It's just not big enough to cool and dehumidify the space. And it doesn't operate at a high enough flow rate. For something like a supply air heating, you really probably don't want to cool that air below 54, 55 degrees. Otherwise, you run a real risk of condensate formation and discomfort with your occupants. And even at 50 degrees, you just aren't able to transfer enough energy through the ERV to make it a viable strategy for supplying cooling to the space. Again, in certain climates, maybe, not in most parts of the United States. So where does that leave us? Well, like I said, it leaves us with good old-fashioned air conditioning systems, recirculating systems by the PHPP's nomenclature. And what that really means in I'm recording this in 2021, what that really means in sort of modern United States is a heat pump system. Now, maybe it's a water source, maybe it's an air source, maybe it's a ground source. In most of the situations that we work in, we're using air source heat pumps. But by all means, there are other types, there are other shapes, other styles, other versions of heat pumps that can work just as well. These machines are electrically driven. They have an indoor part and an outdoor part, and they're typically connected using some sort of refrigerant, and they're able to move or pump heat, thermal energy, from one place to another. So in a cooling scenario, they're able to strip thermal energy out of the space and void it to the outdoor air. And then in a heating strategy, they're actually able to reverse their operation and take energy out of the ambient air and pump it into the building. So these pieces of machinery are actually very well suited to a climate like New York State, where we are asked to heat, to cool, and to dehumidify. As well, they run off electricity, so they're excellent from an electrification perspective. And they come in all sorts of shapes and sizes. They are rapidly gaining traction in the market, becoming very standard on most projects. Here you can just see a couple of form factors. They come in wall-hung units, they come in floor mount units, ceiling mount units, cartridges, drop ceiling units, hidden units, ducted units, unducted units. They come in every shape and size under the sun. So we use a lot of these types of equipment, and of course we're able to model this in the PHPP. Now, if you haven't ever done any heat pump sizing before, the way to properly design and size a heat pump for a residential application, like the one that we are looking at here with this example problem, is to do what's known as a manual J calculation from the ACCA, I don't remember what that stands for, but the ACCA, Air Conditioning Something Contractors of America. I should know that by now. The ACA and the Manual J would be the right method for calculating your loads. Then the Manual S is what you would use to select and size the equipment. And then the Manual D is what you would use to actually design the ducting system. And then there's another manual that I don't remember the name of because we never use it for actually designing your registers and diffusers as well. These would be the appropriate method, the appropriate methodology, and the appropriate reference standards to use when you're designing and sizing the heat pump system for your passive house building. Do be careful not to oversize these heat pump systems, because then you can run into significant cooling issues. Now, there is a heat pump tool for the PHPP. We will look at that in some depth, but this is really for the heating side. So this is the heat pump tool that's available through PHI's website is really for the heating side. We will come back and take a look at that in future videos when we turn our attention to the primary energy and the heating equipment. But for the cooling side in particular, we're just going to be asked to put in some basic information about the equipment that we are desiring to use for our project here. So we'll come back and look at this heat pump tool, of course, but this is not what you would use to size or design a system. The heat pump tool here is really just used to calculate the COP, the coefficient of performance, for a heat pump once you have selected it, once you've designed the system. So again, the right method or the right protocol to actually design a system is that manual J, S, and D coupling. So we'll turn our attention back to the PHPP in the next section, and we'll take a look at modeling these active cooling systems.